Hello, welcome. The first session after lunch is always interesting. But thank you so much for coming down for this talk. So my name is Saptak Sen. I'm in the Azure data platform. It used to be called SQL Server Data Platform. We are brand new. We have been renamed as Azure Data Platform. So I'm a senior product manager, technical product manager in that team. And my focus in last 9 years, primarily within Microsoft, has been distributed computing of various forms. I've done HPC, message passing interface kind of applications, other embarrassingly parallel applications. For last 3 years, I've been focused on distributed data platform. And especially on the cloud, it's becoming one of the, not just the hot topic, but it's required, distributed data platform. So that's what I'm going to talk about today. Before I begin, let me ask you, how many of you already use some sort of, some people call it NoSQL data store? Wow, that's awesome. Can you throw out a couple of names? Redis. Mongo. Awesome. Yeah. So I'm going to start with rational for non-relational. I couldn't put the word NoSQL in the title. Of course, I'm going to use the word NoSQL all around the talk, but NoSQL to me is a very contradictory term, and I'm going to explain soon enough. And I'm also going to discuss the various NoSQL platforms and what are some of the commonality between all these platforms, common criteria or characteristics across all these platforms that's fueling this attention around the NoSQL data stores. I'm also going to discuss about the NoSQL compute paradigm, the low-level compute layer that many of the NoSQL platforms has common. So I'm going to discuss quite a bit about that. And finally, I'm going to do some demos. What's driving this craziness around NoSQL? I call it irrational exuberance around non-relational, right? First of all, especially for companies who want to quickly bring some product into the market, and today's economic condition is pushing them towards a minimum viable product. They don't want to think ahead in terms of where their product or their business requirements are going to be. They have an idea, especially in case of startups. If they have an idea, one of the founders, he's the product manager, he wants to quickly prototype something so that he can go in front of the VCs and pitch it, right? So he wants to craft the minimum viable product and somehow get it to work. The next aspect is minimize CapEx. Again, today's economic condition is driving it so that you can't buy a bunch of servers. That's absolutely a no-go. You spin up a bunch of machines on Azure or AWS, and you build something so that, again, you can pitch it to your business leaders, executives, or venture capitalists. And the other aspect is there's still one consideration that everybody has at the back of their mind. Whatever they're building, it's geared, or it needs to be at least have the potential of hyperscale, because nobody wants to build a product which won't scale, right? It needs to if there are millions of customers tomorrow, it goes viral, they need to be able to support it with the current business plan they are going with. Now, the other aspect is that they also realize as they start up around the idea, that idea is going to evolve quickly. And as it evolves, they need to be agile and need to be able to evolve their technical platform with it. And that's what is the other aspect which is driving it. For example, I have this, if I can get it out, a little fob here. It's called Fitbit. How many of you have this? Any of you? No. So, yeah, from the tweets, it looks like a lot of people at TechEd has this. This is basically a glorified pedometer, right? So it tracks every step that you take, and it has some goals and so on. Now, this is a small company. It's a hardware startup. They launched about a year back with a very minimal set of features. About a month back, they added a feature through a software update, like also track sleep, how well you are sleeping at night and so on. So they can't throw away all their existing data, right? They need to be able to modify their schema and the data store to be able to adapt to new, business evolutions, right? The fourth aspect is the age of what we call DevOps. The clear partition between ops and dev is kind of collapsing. Again, in most companies, now developers carry pagers. If they are creating a service, they are the guys on point to make sure that service is running, so that wall is collapsing. So developers need a platform which they can easily operate. They don't want to, rack and unrack servers, right? It's not in their DNA, right? They just don't know how to do that. They don't know how to, cringe cables. Those are the kind of things you can't expect from developers. So these are some of the business imperatives which is fueling this rush, this gold rush around NoSQL and non-relational data stores. So gold rush is a very interesting word. I am from Seattle, so Seattle was at the center of gold rush, right? So in this madness, the people who benefit the most, you see this plethora of vendors trying to sell all these different fragmented data solutions. So they were the kind of the people who created Seattle, right, actually. Means they sold axes and spades and whatnot to all those people going for the gold rush. And that's how Seattle was created. Let's see, my clicker would work. There you go. So what is NoSQL about? As some of the business imperatives showed, that it's about low cost, at least very low upfront cost. And that's why you see a lot of the solutions are open source, because it has the lure of being, at least on paper, being zero cost. These founders can go to their VCs and say in their balance sheet that, hey, I don't have a line and item for software. I don't need to spend anything on it, but that, whether it's true or not, it's a whole different thing, but at least that's the promise. The other aspect is, you don't have any upfront CapEx. You can do the demo on one virtual machine, and then, again, potentially you can scale up to as many machines as possible. And most of this new breed of businesses, they're pretty much operating out of a laptop, right? So they want to be at web scale. They want to have developer tools, management tools, which are web friendly. Some of the processing or technical criteria. High availability is key, especially when you are designing for hyperscale. Your business, even though you are running out of a laptop, is mission critical. You need to be sure that you can fail over, you're not down for a second. And those kind of aspects are driving some of the requirements like GODR, tunable latency, and so on. So I need to be able to pay so that I can tune the latency between my distributed platform, between the different assets in my distributed platform as my business demands. Performance obviously is at the top of the mind. I'll tell you what's driving performance. In most of the web businesses, the product that the web businesses sell is us, right? The users, right? So we use, most of these services are free. We use these services. We love these services. And as a result, in return, we are giving a lot of information about ourselves. So their main product is to mine that information as quickly as possible and monetize that, either by upselling it back, a whole bunch of products back to us, or selling that information to a third party who can monetize that. So when we are talking about millions of customers, then performance becomes, scale becomes one very key component. We are no longer limited to the number of customers that can walk into a brick and mortar store, right? It's suddenly the world, everybody in the world is our customer. And the last one around performance is tunable and eventual consistency. And I'm going to talk about this a lot more. So there is this new thing, means consistency used to be one of the things which used to be the rock of a data platform. Unless a data platform was consistent, nobody in their right mind would, bet on that data platform. That used to be the case. But in today's age of internet, when you have too much information, you don't need to see all of that information. If you just are able to access a sample of that information, that's enough. I'll give an example. I'm sure all of you have Facebook page. When you refresh your Facebook news feed, do you think every news item from your friends show up? It doesn't. It's just a sample of news items or friends' posts that show up, which could be retrieved within the given time, because they are querying against a distributed platform. So their criteria is to be able to fulfill that query within a certain amount of time and not get all the information to you. So they care more about performance and scale than consistency. They're not a bank, right? The third big category is the data model paradigm. And I kind of alluded to it a little bit earlier. Flexible schema or data first. I was talking about how business plans evolve. They start with a particular schema which they feel today that will meet their business needs. But as the business evolves, and many of these businesses very quickly iterate. They started with something totally different in mind. They end up doing something totally different. For example, Twitter never started off as 140 characters. They were a totally different company when they started off. This was a side project, and that got viral and became Twitter. Low impedance mismatch between programming and data model. That's very important. Again, this is being driven by the whole DevOps culture. So the traditional data modeling role that DBAs or data modelers used to fulfill, that's getting merged with job is also being asked of programmers. And programmers think in a whole different way. They want to be able to almost determine the data structure from within their code. They don't want to do a 7 normal form, right? So a lot of this NoSQL gold rush is being fueled by some familiarity, some perception, some very short-term thinking. Get what you can today. We'll think about how to in the long term. So this brings us to a very important topic, which is called the CAP theorem. It's also commonly known as the Brewer's theorem. Now, CAP theorem says that you can have only 2 of these 3. C is for consistency, A is for availability, and P is for partition tolerance. Now, let me explain a little bit more about what I mean by each of these terms. Consistency, we all know, whoever has a background in data platform, and it's the C in ACID, right? Now, availability is the ability to serve up a result within a given time frame. And partition tolerance is the new aspect which we never had to think in when we had just monolithic data stores. It's the new aspect of a distributed data platform. In a distributed data platform, when you have independent nodes, having just a portion of the data, any update, insert, or especially update and insert, there is no guarantee that the other disjoint or other data stores will be able to know it within a certain amount of time. So the ability to tolerate partitioning of data is crucial. So again, CAP theorem says that you can get any 2 of these 3. So as I was discussing before, think about the Facebook case. They are sacrificing consistency for availability. So they want the queries and the updates to happen super fast for almost 1 billion users. They obviously, because it's such a lot of data, they can't just scale up. So it is a distributed data platform. So those they are bound by. So the only thing they could sacrifice was consistency to an extent, right? And all these are not kind of true and false options. You can have a slider where you give up a little bit of that, you gain a little bit of the other 2. So many large-scale customers means how are they addressing this? First of all, data is sharded. Data has to be sharded. So By word shard, I mean it's partitioned across many nodes. The only way to synchronize those is to do in async mode. You can't let a transaction wait for all the data stores to be updated before the transaction returns. Because in that case, either most of the transactions will either time out or it will fail. So through asynchronous messaging, you need to synchronize all these disjoint data stores. So there needs to be able to support that, there needs to be a sharding layer. When data comes in, it needs to be able to be automatically be partitioned. By automatic, I mean either there needs to be a processor which determines which piece of data goes where, or you need to be able to tell the processor as to how to shard that. And the other side of this coin is to be able to do a fan-out query. So when you are doing a query, it's not enough that the query results come from just one store, because you will only get a portion of the data. And of course, all this has a cost and overhead. In any distributed platform, there are overheads. And sometimes these overheads could be prohibitive. To get around that, people often have a caching layer. So that's where things like Azure Cache or MemCacheDB come in, where common queries which has already been resolved automatically are pulled from the cache instead of going to the raw layer. For example, Twitter had created a special cache for all Justin Bieber tweets, because there were just so many followers of Justin Bieber, and they were all doing the same queries. You don't need to go hit the raw data store again and again to pull that out. You just give the first 100 from the cache, and people will be happy. They'll take like 2 hours going through all those 100 tweets, right? So that's an example. So there are many examples in real-life customers, Facebook, MySpace. Even people have implemented this even with Service Broker and SQL Server. So this is a pattern, right? This is an architectural pattern which can be implemented on any OS, any data platform. People have done it with MySQL. People have done it with SQL Server very successfully and have been running it for years. Now, we have started codifying some of these patterns in our platform. One of the examples of this is Azure Federated Azure SQL Federation. If you haven't seen Azure SQL Federation, it does exactly what I described. To your query, it looks like a single data store, but it can pull data from multiple partitioned SQL Server running on Azure. The same thing when you are updating or inserting data. You provide the partition logic, and it partitions it and puts the data across multiple nodes. So that's the query. What about the data warehousing layer? Of course, you can pull from all this sharded data store and load it into a traditional OLAP data store. And a lot of customers do that. And OLAP data stores also can be sharded or partitioned. A case in point is we have a case study with Yahoo, where Yahoo has a partitioned OLAP cube, which is, in the last count, was almost 26 terabyte. Obviously, they can't put a 26 terabyte OLAP cube for that layer in one machine. So it's partitioned across 12 servers. A new option is also people are creating data warehouses in things like Hadoop. Now, remember, there are certain things to keep in mind in both of these cases. Now, Hadoop is a batch platform. It can hold a lot of data, it can scale pretty well, but it's a batch platform. By default, it doesn't contain any index, which is its weakness as well as its strength. But of course, there are other solutions, and I'm going to talk about some of the solutions which are trying to address that. So the philosophy around Hadoop is that, I put all my data in a partitioned cluster, right? And when I fire a query, through a MapReduce job, it goes and touches every bit of that data on every machine. So actually, the head of the drives go and touch every bit of that data on every drive in the cluster. Now that is cost prohibitive in terms of I/O. The first reason, 30 years back, we created indexes is that going through or moving that head or whatever across all those bits takes a lot of time. It slows things down. But the plus of this is you can do ad hoc queries. Most indexes are designed for a certain predetermined queries. But if your data is sitting raw on Hadoop, you can pretty much fire any query. It will go touch every bit and get you the answer. It might be a few hours later, but it will get you the answer. But whereas if you have a set of existing schema and thereby a set of existing indexes, primary and secondary indexes, that means only certain queries, it's optimized for a certain set of queries. And both has its pros and cons. Now, why am I discussing all this? Because it's not a one solution fits all situation. So be very careful when somebody comes and pitches that you can replace everything with Hadoop or any one, MongoDB or whatever it is. Or on the other hand, you never want to hear about all this. You can do everything with your SQL Server or MySQL, whatever it be the case. The truth is somewhere in between. You need to kind of think through a little bit in the long term as to what your data platform architecture is to fit the right solution. Now, the next part is, so what did we learn from all these scenarios? Some of the key aspects today that we cannot discount anymore is, for example, high availability, the ability to scale out, the ability to partition data, have quorum, be able to do retries, automatic reprise, and also the requirement of eventual consistency. And some of these features are becoming mainstream in all data platforms. You'll soon see a lot of these capabilities are becoming standard in all data platforms. And lastly, again, the ability to quickly grow and change, the elastic scale is very important. And this is where cloud comes in. We talked at length about the need for low or very low CapEx. So elastically be able to scale to your current business needs is very important. Flexible and open schema. For example, means raw data on Hadoop has no schema. It's traditional data stores have schema on write, but in Hadoop it's schema on read. You apply the schema while you're reading out that data. You'll hear the term unstructured data a lot. I'm not a big believer in unstructured data. I say it's yet to be structured data, because all data has structure. The only data which does not have structure is the cosmic background noise that you see when your TV is not tuned into a station, the white ghosting. That's the only unstructured data. Every other data, whether it's sitting in unstructured or yet to be structured data store or everywhere, has structure, and that structure will be applied at some point. So all this are becoming standard in our data platform. Now let's look at the set of data models that's driving this. At the top, you have the simple key-value pairs. Somebody said they use Redis, right? It's a great solution for where your business needs are met with single key-value kind of a situation, and it's very scalable. That's its strength. It's optimized to be scalable. It's the same thing about Azure caching. There are wide sparse column sets like Azure tables. There are others like HBase, Cassandra. They are of the same category. Then there are blob store for other kind of data like images or raw text and so on. Azure Blob Store is a great example of that. There are JSON document stores, and you have MongoDB, Couchbase, React, RavenDB, which is implemented in .NET. So, for example, also MongoDB, by the way, works very well on Azure, so you should check it out. It's a simple, 3-click situation to deploy MongoDB on Azure. So that's a JSON document store. And the document store has a certain set of promises that it makes. For example, dynamic schema. The ability to not be tied to a single schema. You basically have a database, and within that database, you have collections of JSON documents. And each JSON document can be of a different schema. So that's its promise. So the point is that they're making is that today your business needs are, say, foo. And you have a certain schema for that foo. But tomorrow, if your business requirements extend or change or evolve, you can change the schema without having to create a new database and new schema. So that's promise. Now, that has its, downside also. The downside is when you are doing query from your application, you have to pretty much walk the whole document tree to understand the schema. You don't have a standard document tree, so you basically are implementing the schema in the application level. So that has that can make your application fragile. It can make it much more complex. Then, of course, the graph databases like Neo4j, GraphDB, Hypergraph, Stig, all those. Neo4j, again, works very well on Azure. You should check it out. Then there are object stores like SQL Server and SQL Azure. And then there are extended relational, and I'll talk about extended relational soon. Now, one of the common things across all the NoSQL or non-relational, at the core, many of them use MapReduce as their key computing paradigm. They might have other higher-level abstraction, but at a very low level, they use MapReduce. Because MapReduce works very well for distributed data stores, and I'll explain how. Now, let me explain MapReduce in the context of Hadoop. So in this slide, I'll quickly explore the architecture, very simplistic architecture of Hadoop. So Hadoop basically has the storage layer, which is the HDFS layer. And then you have the MapReduce layer. In the HDFS layer, at the crux of it, you have the data node services or daemons, whatever you call it, running on every node, and multiple of those running on every node. And then there is a name node daemon or service, which contains the metadata, which determines which block of data is where, which contains the information around which block of data is there. So it basically provides a virtual namespace which looks like a file system to the application. When your data is sitting across many machines and many drives in those machines. At the higher layer, you have the MapReduce layer, and that is the computation layer. In the MapReduce layer, again, you have these task tracker daemons on multiple nodes. The task tracker daemons or services are just bootstrap executables which can start up a process. And it can also communicate with the job tracker around the progress of the tasks, as well as provide a heartbeat to make sure the name node and the job tracker knows that those nodes are available, right? Now, let's go a next level down around MapReduce. Now, as the name suggests, you obviously have in MapReduce mappers and reducers. Now, you see many of those boxes are in different colors, and those are not just random colors. The gray color is the only one which is absolutely necessary for you to implement. The rest, the orange are optional, and then the greens are, even less optional, and then the black you don't have to worry about. So in any MapReduce program, your name node, the job trackers fire up or bootstrap a bunch of mappers when a job is initiated. You have a MapReduce job which gets submitted, sitting in the queue, and when the job tracker initiates that job, it instructs all the task tracker services or daemons to spin up mappers. Now, mapper is a code that is implemented by you. Now, what job tracker also does to the mapper is it provides or starts reading up the shard of file that is sitting on that particular node and feeding it into the mapper as key value pairs. Typically, it depends on your serializer and deserializer, but typically the mapper gets key as the file offset of a particular string, and then the value is the actual string, right? And in case of binary files, it could be a bunch of bits, right? Now, as all these mappers across all these clusters are going through this input, they can transform it and then emit it out as another set of key value pairs. And how they transform it within the mapper is determined by the code that you write. Now, later I'll talk about higher abstraction layers which automatically generates code to do this. So you don't have to write the mappers yourself, because if you fire a SQL-like query in Hive, it automatically generates the mapper code to be able to do this. Now, once the mapper emits it, for the time being, let's ignore combiner. We'll come back to combiner. It goes to the partitioner. And partitioner is part of the framework itself. Now, partitioner with the MapReduce framework does do a shuffle and a sort and a shuffle. It sorts all the buckets of key value pairs by the key and puts all the key value pairs with the same keys together and shuffles in the process to make that happen, and then provides it to the reducer. So each reducer only gets a bucket or a list of key value pairs with the same key needs to always land on a single reducer. The reason it needs to land on a single reducer is then in the reducer, you can write the code on how to aggregate all that list of key value pairs with the same key. And then, of course, the reducer aggregates it and emits as key value pairs, aggregated key value pairs, which is then written out to HDFS. Now, I know it at this point it's sounding very abstract if you're already not familiar with it, but in a couple more slides, I'll explain it with a business case so that it's clear. The reason I'm going into so much details about this is you need to understand the computing paradigm to appreciate what are the right class of problems for this kind of platforms, right? So that is the intention. Now, combiner, I said I'll come back to the combiner. Combiner can be the same as reducer. It can do also the aggregation, but it does the aggregation before you have to do the shuffle. Shuffle is very I/O, has a huge I/O cost, network I/O cost, because whenever you think about shuffle, it's moving data across the network. So if you can aggregate the data before you hit the network, then there is less data to move around the network. So it's an optimization part in combiner where you aggregate it and then do the shuffle. So most of the time, combiner is often the same code as reducer. It's doing the reducing, or it's reducing locally on a per task tracker basis. Okay. Now let's look at it, with another picture, right? So think of let's say there are 3 mappers, and each mapper is reading from what we call the input domain, basically a shard of the file. It's scanning and pulling that in. And as it goes in, it does the transformation, and that is the code that you have written again. And then it emits it as intermediate data. And that intermediate data in Hadoop is designed to be kept in memory, because again, you don't want to write it to disk as much as possible, or you try to avoid writing to disk as much as possible because it's expensive. Because anyway, the shuffle stage, which is between the intermediate domain and reduce, will move all this data over the network to the reducer. You don't need to write it there. So the reducers then gets buckets of this MapReduce key value pairs and then does the aggregation. And then finally, after multiple stages of this, you can write it out to the disk. So this is at the core of many of the distributed data platform technologies. This very common paradigm is at the core. There are other some other efforts to do something a little different, where you shard by documents and so on, so you can only look at a particular document. But they have severe limitations that you need to know about. So let's look at some code very quickly, so to make it very clear. So this is called a MapReduce driver. By the way, this is Java code, but if you are comfortable with C#, this should, at least the code syntax should look very similar. It almost looks like pseudocode, so it shouldn't be too hard to understand. So let me try using the new laser pointer technology here. So first of all, this is the main method, which bootstraps your mapper. Basically, your mapper and reducer. This is the new job. So first of all, you set the configuration here, and then you set the class and the method that will do your mapper and your reducer. Again, combiner is optional. In this case, you see that I'm setting the same method as the reducer here, and then after I've bootstrapped it, I also set the configuration around where I want to read from the file. By the way, this is the path inside the HDFS namespace, which is a virtual namespace. This is not a real, your NTFS file path. If your data is in NTFS, MapReduce doesn't know about it. It has to be registered in the virtual namespace of HDFS to be able to locate it. And then it also sets the output path. Okay. So this is just setting up the configuration. This is the bootstrapping the whole job. The next part is the mapper itself. In the mapper, what we are trying to do is we are reading, let's say, a huge XML file. The XML file physically is partitioned and sitting across maybe hundreds of disk drives across, say, tens of physical machines. To the mapper, it's got a single path in the HDFS namespace. It queries the HDFS name node to find out physically where each of those blocks of which comprises that file are sitting on. Right? And then for the string that I get, which is the value, I use a function to transform XML into a map. And then I parse through it in this setup and replace and do any kind of transformation that I need to do. And once I have done that, I've basically removed the spaces, removed single quotes, and clean up everything. Then I'm extracting each string in that XML file, and then I'm emitting that back. This is the most important line, context.write word. Word is actually the string within the XML file, and 1 is basically the integer 1. The reason I'm emitting the integer 1, I'm basically signifying the number of times I've seen that word in that set of in that snippet of XML file that mapper has seen. Now you can think thousands of these mappers are doing exactly the same thing. They're going through a portion of the file, taking out each of the words and emitting it as key value pairs, where key is the word and the value is the integer 1. Right? Now, in the meantime, once it gets emitted by the mapper, it gets sorted and shuffled so that all the key value pairs with the same key land up in one instance of the reducer. There are multiple reducers working across the cluster. And each reducer gets a bucket of this. And then I just go through a loop counting all those ones or the values for a particular key, and I write the value. So this is, you've just experienced the hello world of MapReduce. This is the hello world program or hello world equivalent of MapReduce, where you are creating a histogram of the frequency of words in a particular text file. And this is very commonly used in many, many real use cases. But, just as an example to get that. But what after word count? What about some of the complex thing you want to do? Even something simple as joins. How do you do joins like you do in SQL with this kind of a bare bone infrastructure? And that's where the abstraction level layer comes in. One of the common, very common abstraction layer, especially on top of Hadoop, is known as Hive. How many of you have used Hive already? Okay, no. So Hive is, the good news is that you'll be very familiar with Hive once you see it, if you've done SQL. And it automatically generates the right MapReduce job and multiple stages of that to fulfill that query, right? Then, of course, you can do much more complex stuff like machine learning. A lot of the customers are using it to do data transformation. They have large amounts of data sitting on a partitioned data store. They want to basically do transform of the extract transform load. They want to transform across that data. They want to, they have very noisy data. They have to do cleanups or whatever. They want to do feature extraction, whatever they want to do. By the way, I missed one thing. There is a great book, and it's a free book actually if you search. It's called Data Intensive Text Processing with MapReduce. That's the author's name is Jimmy Lin, and if you search Bing, you'll find the PDF of the book, and it goes through case study or real life scenario after scenario, how to solve that with MapReduce. So if you're more interested in this, please look at that. So let's look at one simple situation, one simple example, summarization. Summarization is a very common pattern in any query language, where you want to do a group by, right? It's as simple as doing a group by. How will it manifest in MapReduce? How will it actually work? So you have the data nodes, let's say, and each data node has a file. Let's think these are CSV files, right? And they have the customer ID, the zip code, and the amount, and a random set of this data is distributed all across the different nodes. Now, the mapper starts reading this, of course, and the goal is to get the cells, sum of cells, grouped by zip code. It's a simple enough query. So the mapper, as it reads through it, it determines that the zip code needs to be the key that it emits to the reducer. Then only the reducer can sum it up, right? So every time it sees a particular zip code, it puts it as the key so that the sort and shuffle phase will aggregate all key value pairs with the same zip code and send it to a particular reducer. So in reducer, you have the shuffle and sort happening here. Now all the particular zip codes are in the same place, and you then just sum it up. And you do multiple stages of this, because sometimes it can spill over to a additional reducer, because one reducer may not be able to handle all the number of zip codes. Now let's look at a demo and see how this all works. First of all, let me fire up Windows Azure portal. Okay. Now, Windows Azure portal, among many things, it can very easily, oh, you can't see anything. Sorry about that. I don't know. Okay. Should have told me. What's happening? Sorry, but we have signing out. Kidding me. Let me duplicate the screen so that I'm able to see what's going on. Okay. Interesting. Okay. Give me a second. I'm trying to sign in. So while I'm signing in, one of the things I want to stress is that about 2 years back, when we started on this journey, my management asked, hey, can you stand up a Hadoop cluster and find out how simple it is, how it works and everything, right? So because internally at Microsoft, we have a similar distributed data platform, but it wasn't Hadoop. We have, hundreds of thousands of servers in that distributed data platform, but Hadoop was something new to us. So I stood up a cluster of 2 nodes first. It was simple enough. I copied the config files, I configured it. But as I started configuring larger and larger clusters, it became very, very complex because of all the hand plumbing that you have to do. And I was given about 56 nodes and run some benchmarks. By the time I was at 10 node, it's become so difficult to manage it by hand that I almost was ready to give up. But we persevered and we tested and got all the feedback. But so this is the Azure portal. In Azure portal, you can create Hadoop cluster extremely simply. For example, these are the 2 Hadoop clusters which I already have running. If I say new and go to data service and HD Insight, I can create a Hadoop cluster. And from those days, those nightmare-ish days, coming to this experience, it's like, it's like heaven and hell difference. In under 10 minutes, I can create a cluster here of a size of my choosing. And then I can start running my workload. The other great thing about this is tied to another non-relational data platform we have, which is the Azure Blob Store. Now, Azure Blob Store has been around on Azure for a long time. And a lot of our Azure customers, especially if they are doing mobile apps or whatnot, they are storing their log files on the Azure Blob Store. So what they are doing right now is spinning up a Hadoop cluster, mounting the Blob Store, doing analytics on that data. Once they're done, they write it back into the Blob Store and spinning the cluster down so that they don't have to pay for that massive parallel infrastructure, computation infrastructure that they just brought up, did the computation, and then spun it down, right? So that's the great part about Azure. Remember some of the tenets that we were discussing. Low CapEx as well as low OpEx. That's one of the key things that's driving. Not only that, you can go to store and you can select new items like MongoDB, for example. Yeah, I have to use another account. This account, I can't. But this morning, in less than 3 clicks, I created a MongoDB data store on Azure and started using that. Now, let me go to the next level. Let me actually show you running something. So, if I click on Manage Cluster, I can actually see the cluster here. Okay. Let's try that. So, for obvious reasons, I always get my passwords wrong on the stage for some reason. Either I'm too careful or whatever. So, if I log into it, what I see is that it's a web portal which lets me monitor my jobs, which lets me run new jobs, submit Hive queries, and so on. Now, on the cluster, what I did was I ran a bunch of Hive queries. So these are the Hive queries I ran. And before that, before I actually describe the Hive query, what I want to first show you is the data that I'm using. So the data is basically 30 years of stock data. So let me spin up Cloudberry, which is sitting on the Azure Blob Store. And this is text data, so you can think of it as unstructured data. So if I go here, now, to prove that it is actually the Blob Store, let me grab the Blob Store key from here. So now I'm seeing the contents of my blob store. Now this blob store is mounted by my cluster, and this is my data. As you can see, there's a lot of CSV files. This is 30 years of end-of-day stock data, essentially. Now, what I did was, on top of that, I created a Hive table. You see this is the location to store. ASV means it's on Azure Blob Store. I'm creating a schema on top of the unstructured data. Then I can fire a SQL-like query. This looks like SQL, but this is actually Hive query language. And when I fire the Hive query language, it in turn generates the MapReduce job, that the kind of MapReduce job we just explored in detail. And after it runs the MapReduce job, it returns back the result. I have an option of writing that result back to disk. So what in this case I do is, this is all the ticks, right? Every tick that has happened over last 30 years. That's a lot of data. I cannot possibly look at that data with my naked eye, so to say. What I did was I ran a query and I aggregated it. So this is the Hive query I use. So insert override, and then I do a join between the stock price data and the dividends. And then I write it back into HDFS. And once I've written it back into HDFS, that big data has become aggregated small data, which I can now start analyzing using my standard BI tools. So let me show you how I do that. So this is plain vanilla Excel. And I use a technique or capability called Data Explorer in Excel. Right now, it's an additional plugin. Now, I can connect to many different data sources from Data Explorer within Excel, but I can also connect to Azure HD Insight. So here I'm going to put in the name of my cluster, and it's now going over the internet to show me all the results. So there's a long list of files this is sitting on the Azure Blob Store. By the way, Azure Blob Store is also a distributed data platform which we are mounting on from HD Insight service. Now I'm going to pick out the output of the job, the Hive query that I showed you. So this is the output file, and that is sitting on HDFS, which is mounted on the Azure Blob Store. And to pull that down, as you can see, it is sitting again as just a CSV file. Now I need to structure it. From Data Explorer, it's very simple to do it. With a single click, I have now put some structure back into it. Now I can rename the columns. Now what it is doing is, it's doing it on a sample of the data. So this is the symbol. This is the year. These are the three prices. This is the highest price for the year for that particular symbol. This is the lowest price of that year for that symbol, and this is the average price for that symbol. Now, in this case, let's say I'm not going to use the highest and the lowest. I'm just interested in the average. So I can hide the columns from here. And then I can rename this to price. And this to dividend. Now you can see that some of the rows doesn't have numeric values, because especially in the dividend column, because those stocks didn't pay a dividend in that year. So how do I clean this up? So I can clean it up that way. Now, once I've done this, let's say I want to limit my analysis to only the stocks in, I'll stop the download here because I'm not yet done transforming this data. I just want to limit this analysis on the set of symbols which are in S&P 500. Any of you can shout out which are the symbols in S&P 500? I'm just kidding, you don't have to, I can look it up here. So what it's doing is, it's going ahead, doing a search on the internet and finding out all the data sets that might be of interest and match that query that I just did, S&P 500. And when I clicked it, it pulled it down. Now I can mash these two data sets. Now I can go to filter and shape. I can drop the ones that I'm not interested in, the columns. For example, I like the ticker symbol. That's the field I'm going to do the joins by. I like the company name. I don't want this, what kind of filing. I want the industry, but I don't want the sub-industry and the dates filed and the keys. This I can hide. Now I'm going to join these two. I can say merge, and you can see this is my first one, my proprietary data set, which I got from the aggregates after it was done on Hadoop. And this is my the internet or the data set I got from the internet. Now at this point, it's going and merging the two data sets. Now, of course, I don't need the duplicate symbol. I can expand it. Now, what I've got is, I have the 30 years of stock tick data, right? But I didn't have the name of the company, the industry they're in. I didn't have the location. Neither did I have the information whether they're in S&P 500 or not. Now I have it. Now, you'll see that some of the columns are null for some of the symbols. The reason is that those symbols are not part of the S&P 500. So I can very easily filter this out. Now I've restricted my data set to just S&P 500. At this point, I'm ready to load this into a OLAP model. Now, in this case, the OLAP model here is the Power Pivot model. But once I build a Power Pivot model, basically it's a tabular model. I can have the same tabular model in SQL Server Analysis Service and refresh it there. It got all the information and shaping and so on. Here is this little link called load to model. If I press this link, it is going to load it into the in-memory Power Pivot model, which is a OLAP cube. Yeah, now it's loaded. To prove that, I'm going to go to Power Pivot and say manage, and it should show up. If I go to diagram view, here is my single table Power Pivot model. I can have multiple tables, create relationships, I can create hierarchies, and so on. Now, I can start visualizing with this. So if I go to insert, and let's say do a map, for example, in this case, by map, I'm inserting a GeoFlow view. I can start visualizing on this data. For example, the address is where the locations are. So let's say this is a city. I say map it. And then I want to do it, let's say, on price. Not there. Price. Price should be in height. Sorry about that. Remove it from the category. And now you see it shows, companies where had the, so on the map now I can visualize the data. Of course, I didn't set the right data type for price. It's still text. That's why it's only giving me a count. But I could have done other things if it was numeric. I have set the right data type in the model, Power Pivot model itself. So the point I'm making is that in any data infrastructure, you have data store, irrespective of its non-relational or relational. You have a data store. Then you need a layer, say, for fast queries, a caching layer. And that's where Azure Cache comes into play. And then you need a data visualization and data analytics layer. And that's where things like Power Pivot and SQL Server Analysis Services comes into play. So you have to think about all the different components. Just one component in isolation is not enough. Just to wrap it up, flexible data is good, but as I said, you need the option of providing fixed schema. You cannot always have all the schema logic inside your application. Procedural scale-out is great, but you need to have a declarative language suited for across different data models. You can't go to different data stores for every different data type, right? And finally, eventual consistency is good, but you also need to be able to tune that. Tunable consistency is what is required, because you can't change data stores based on what kind of consistency you want. Now, these are some of the things that we covered today. Why we need a non-relational data store, what's the rationale behind that? the paradigms, all the different types of NoSQL data stores, of course, we couldn't dive in. Means there are sessions on MongoDB and others which dives into that particular technology in this conference, so go attend those. But in the limited time, we couldn't cover. We covered the basis of most of these non-relational data stores. We saw, how some of these paradigms address some of the common business problems. And then, of course, we walked through the demos. I hope it was time well spent. And there are plenty of other information. We actually have a white paper and on this topic. And also, these are some of the resources. One of the key resources is Microsoft Virtual Academy. There, right in the middle. It lets you do hands-on lab. It walks you through different videos through a curriculum path to develop a certain skill. And then follow our SQL Server Twitter account. And Channel 9 will have all these presentations on Channel 9. And finally, please make sure you fill out the evaluation. Any kind of feedback is very important to us. And thank you so much for attending the session. Thank you.